morning one and all. Myself Durga Bhavani, working as an assistant professor in Department of IT in Mallareddy Engineering College for Women. Today I would like to explain a topic from compiler design. So in compiler design we have different types of parsing techniques. One is the top-down parsing and the other one is bottom-up parsing. So coming to top-down parsing, in top-down parsing we parse the input string from top to bottom, whereas in bottom-up parsing we have to parse from bottom to top. So in this bottom-up parsing we have important algorithms like important parsers like shift reduce parser. In bottom-up parser we have shift reduce parser, operator precedence parser, LR parser, and LR parser is again subdivided into different types like LR0, LR1, SLR, SLR1, CLR and LALR. So in this LR parsers are used to parse a large amount of grammars, and in this LR parsers we have like the L indicates like you have to parse the input string from left to right, whereas R indicates in LR parsers, L indicates you have to parse the input string from left to right, whereas R indicates you have to construct the parse tree rightmost derivation reversely. And for constructing LR0 parsing, we have to follow different types of steps. The first step is you have to check whether the given input string is following the grammar of the language or not. And the second step is you have to check the ambiguity of the grammar. And the third step is you need to add some augmentation protection to the given grammar. And the next step is you need to create canonical collection of LR0 items. And the next step is you need to draw a data flow diagram. And finally we need to construct the LR0 parsing table. So these are the steps which we need to follow while using LR0 parsing technique. So we have taken one example. The grammar we have taken like S determines AA and A determines AA or B. So for this grammar we are going to construct the LR0 parsing. So first step according to LR0 parsing is for this given input string you need to write the context free grammar. So context free grammar is nothing but a grammar which consists of a set of terminals and non-terminals. A context free grammar is nothing but if a grammar consists of set of terminals and non-terminals, then that grammar is termed as a context free grammar. When coming to terminals, terminals are nothing but the small case letters are called as terminals, whereas the uppercase letters are termed as the non-terminals. So here the given example which we have taken consists of terminals as well as the non-terminals. So this grammar we can consider as a context free grammar. So our first point has been satisfied in this. When constructing the LR0 parsing, the first step is you need to check whether the given input grammar is context free or not. So first step is satisfied. And the next one is checking the ambiguity of the grammar. So to check the ambiguity of the grammar, the meaning of ambiguity is from a given grammar, if we are able to construct more than one parse tree, then that is called as an ambiguous grammar. So given grammar is not an ambiguous grammar. So for checking that we have a different process. So when learning about ambiguity we are going to learn that. So here this grammar is not an ambiguous grammar. And the third step is you need to add the augmentation protection for the given grammar. So the meaning of augmentation protection is if you are adding a new protection in the grammar, then that is called as an augmentation grammar. So this is our grammar. So for this grammar we need to add a new protection for that. So when you are adding a new protection, you need to consider the starting symbol of the grammar. So the starting symbol of the grammar is S. one more new production that I am terming as S dash. So S determines, sorry, so the new production we are considering, our starting state is S. So we are writing as S determines S dash is our new production. So the augmentation production is now S dash determines S, S determines A determines AA or B. So this is the production which we got after adding the augmentation grammar. And now the next step is create a canonical collection of LR0 items. So canonical collection of LR0 items is nothing but placing a dot in the first position of your left hand side grammar. Canonical collection of LR0 items is nothing but placing a dot in the left hand side production of the grammar in the starting position. If you place a dot, then that is called as a canonical collection of LR0 items. So now for the given grammar we need to create canonical collection of LR0 items. Then the grammar will become as S dash determines dot S, S determines dot AA, A determines dot AA or dot B. So this is our canonical collection of LR0 items. And next step is we need to draw a data flow diagram. So the next step is we need to draw a data flow diagram. So for drawing the data flow diagram, we have created a grammar with adding augmentation production as well as canonical collection of LR0 items. So with the help of that you are going to create a data flow diagram. So for drawing the data flow diagram, we have taken, you need to consider the grammar S dash determines dot S, S determines dot AA, A determines dot AA or dot B. So this you have to name as a state I naught. So as you need to start from the 0th state, so we are you have to name it as I naught. Now what we have to do is you need to reduce that, you need to reduce the grammar. So here reducing the grammar is nothing but you need to place this dot at the end of this symbol. At the end of this symbol. So now what we have to do is now I naught or S. On the first grammar you need to do this. So what it will become as S dash determines, you need to just shift the dot to the next position. So it becomes like S dash determines S dot. So now this we are naming as state I1. And now on symbol, coming to the next production, as the first production is completed, we are going for the next production. So on symbol A, as we are having A as the first symbol here, so on symbol A, if you do the this, then it becomes as S determines A dot A. So it becomes as A dot A. And now here after a dot we have here non-terminal. So when you have non-terminal, what we have to do is you need to write all the productions which this non-terminal consists of. So for this non-terminal we have productions like A determines dot AA and dot B. So this is termed as state I2. And now as this production is completed, we are moving to the next production. There we have a symbol A. So when we do that, it will become as A determines A dot A. So again after dot we are having a non-terminal. So you need to write all the productions of this related to this non-terminal, that is A determines dot AA or dot B. So now this we are naming as state I3. And now from the given grammar, everything has been completed. So now we need to move to this things. So first we have I1 already the dot is placed at the end of the production, so I1 is completed. And coming to I2, S determines A dot A. So after dot we have a symbol A, so you have to do this on A, then it will become as S determines A dot. So this is completely done and we are naming it as state I4. And here in this we have one more production, and in that production we have like on small a we can do. So on small a if we do, it will become as A determines A dot A or dot B. So this production is already there in the state I3. So what we can do, you can redirect it to the state I3. You need not write a new production, you can redirect it to here. And the next one is on symbol B. On symbol B if you do, A determines B dot. So this we can name as state I4. So in this way you have to do all this productions for that, and then we have to draw the parsing table for this. So parsing table is based on the data flow diagram, and then we have to parse the input string by taking one simple parsing string. We need to parse the input string. That's it. Thank you.